Quantum dynamics in a tiered non-Markovian environment. The present paper introduces a new analytical method for studying quantum systems which are in tiered environments. Amir, care to explain what a tiered environment is?
Thank you, Erik. The motivation for this paper comes from a frequently occurring situation where we have a system of interest that we can make measurements on. This system is coupled to its immediate environment, and this immediate environment in turn is coupled to a wider universe. This is what we call a tiered environment. This includes many examples of discrete quantum systems interacting with an optical or a mechanical resonator, such as NV centers on diamond cantilevers, where the NV center is our system of interest, and the cantilever is its immediate environment, which is damped by the bulk. Other similar systems include quantum dots on carbon nanotubes, nanomechanical resonators coupled to quantum dots or superconducting qubits, and superconducting circuits QED. Another, maybe more complex example is the energy transfer model in photosynthesis in bacteria, where our system consists of a few chlorophylls. Those chlorophylls are held by a protein scaffold, being their immediate environment, and the vibrations in the scaffold is then damped by the surrounding water, i.e. the universe.
That sounds interesting. I understand that you model the immediate environment in a non-Markovian manner, while the wider universe is modeled by a zero-memory bath, simply using Lindblad operators that act on the immediate environment alone. Strictly speaking, Lindblad operators should only move you between energy eigenstates of the system plus environment, and not only environment. How do you justify your model?
This is a very good point. Well, of course you are correct. So this model is indeed valid when the coupling between the system and environment universe are weak. Other than that, there are no restrictions. The system Hamiltonian can be whatever, including time dependent, and the coupling to the immediate environment can be quite general with no restriction on the spectral density.
Very well. And what do you find? How does this additional environmental tier affect the system?
We find that the effect of adding a wider universe, or a second tier, effectively modifies the response function of the environment by adding a cutoff to the response, but in a manner that cannot be accounted for by simply having an effective or a modified spectral density. Also, we find that the steady state of the system differs from the thermal state of the system in the universe's temperature, as shown in our figure 2, even in the very weak coupling limit. This came to us as a surprise, but it is validated by exact numerics. Also, we provide an expansion of the system dynamics in the system-environment coupling in the presence of the wider universe, and show that it falls back to the standard time-convolutionless expansion when there is only a single tier.
Thank you, Amir. I also understand that this method remains applicable when the environment has a few dominant damped modes as well as a smooth background, which sounds very useful.
Thank you. Hope you guys enjoy reading the paper.